Seminar series. Today, the Delta Science Program, Ecosystem Restoration Program, and the Surface Water Ambient Monitoring Program jointly present Scott Brandenberg and Jonathan Stewart from UCLA. Professor Brandenberg earned his BS from Cal Poly San Luis Obispo and his MS and PhD from UC Davis. He joined UCLA in 2006 and is currently the Vice Chair for Undergraduate Studies in the Department of Civil and Environmental Engineering. He is the author of many technical publications and the recipient of multiple awards, including the Shamshir Prakash Research Award and the Arthur Casagrande Award. Professor Stewart earned his BS, Master's, and PhD degrees from UC Berkeley and joined UCLA in 1997. He is currently the chair of the Department of Civil Environmental Engineering and has authored over 150 technical publications and received multiple awards, including the Walter Huber Civil Engineering Research Prize and the UCLA Distinguished Teaching Award. So please join me in welcoming Dr. Brandenberg and Dr. Stewart to the Delta Science Seminar.
All right, thank you very much for the introduction. I'm Scott Brandenberg. Might be a little bit ambiguous. Both of us were introduced at the same time. So the short one is Brandenberg, the tall one is Stewart. I'd like to thank the Delta Stewardship Council for having us come to give this talk on what I think is a really important issue for our state, the seismic performance of levees. And we're going to be talking about two different projects today. One of them is field tests on studying the behavior of peat. So a lot of levees in the Delta are founded on peat soil. We don't know much about its seismic behavior. And so I'll start off by presenting this field test and talking a bit about the behavior of peat. And then Professor Stewart will follow up and talk about analysis of some case histories of a levee system that was shaken by 2 earthquakes in Japan. And we've been developing fragility functions to look at rates of damage of those levees. If you have any questions about the technical content of our presentation, please feel free to interrupt along the way. I know that this is a pretty sensitive issue, highly charged. If you have other questions that go beyond the scope of our presentation, we're certainly interested to entertain those questions, answer them if we can, but please hold off those questions until the end so that we can get through the main content of our talk first. Okay, the outline of the talk, first I'll talk a bit about a background on delta seismic risk, and then I'll present some laboratory testing of post-cyclic volumetric strain of peat. This is a new mechanism that we've been studying that nobody's really considering right now in evaluating seismic behavior of levees. And it's the motivation for the field test that we did. So then I'll go into the field test showing the model embankment that we built, and I'll show a video of the shaking, and then I'll hand it over to John to talk about the fragility functions based on these Japanese case history. All right, I'll start with the seismic hazard background. This is a map that shows, I feel like I'm kind of in the way of the people here. This is a map that shows the major faults in the San Francisco Bay Area and the Delta region. There are really a couple of different sorts of hazards that we are concerned about. There's some major faults like the San Andreas Fault here or the Hayward Fault here that could produce earthquakes with magnitudes in the 7s or maybe even 8 for the San Andreas Fault. Those do contribute seismic hazard to the Delta, but there are also smaller faults that are further east in this region and even within the Delta itself that are capable of producing earthquakes with magnitudes in say, the mid-6 to 7 range. And those also pose a significant hazard to the Delta as well. For reference, the 1989 Loma Prieta earthquake was off the southern part of this map, so it wasn't, very close in the Delta. Based on all of those faults that might cause shaking in the Delta, seismic hazard maps can be formed that show the probability of exceedance of a certain ground motion level. In this case, we're looking at maps of the peak horizontal acceleration for different return periods. This is a 100-year return period, so that's a ground motion that has a 1% probability of exceedance in any given year. And if you look at the western portion of the Delta here, kind of this blue stripe, that's 0.15 to 0.2 G. So 1 G is, the acceleration of gravity vertically, if you had 1 g of horizontal acceleration, it would be like somebody pushing on you with your own, body mass, that much force. So we're looking at, 0.15 to 0.2 g in the western delta, and around 0.1 to 0.15 g in the eastern delta. When we go to a longer return period, these are less probable ground motions. So this is, the map on this side shows a 500-year return period, or a 1 in 500 probability of exceedance in a particular year. And the ground motion levels go up in the western part of the delta to around 0.35 to 0.4 g, and as high as 0.2 g along the eastern margin of the delta. So this is not an extreme level of seismic hazard. It's not like what you would see if you were right next to the Hayward Fault or the San Andreas Fault, but it certainly is enough seismic hazard that we worry about the influence of, oh, now there's a little echo. All right, I'll have to get used to that. The influence of earthquakes on the delta levee. It's okay if you want to leave it.
No, you tell me. Somebody
Can everybody hear me okay without the other?
Need the mic.
You need the mic? Okay, go ahead and turn it on. All right.
There you go.
Okay?
Yeah.
Very good. Okay, and the big reason why we're worried about seismic hazard is related to land subsidence. The delta is composed of a lot of peat soil. That peat has biodegraded and eroded over time, so the interior of many islands are now below sea level, whereas the channels are roughly at sea level. So if there's a breach of one of the levees, the island fills up with water. There's a lot of accommodation space in the delta that's empty now. So if multiple levees were to breach during an earthquake in the delta, enough water might flow in to reverse the flow direction and bring in saline water, in addition to inundating farmland and wildlife habitat. This is a pretty striking image that Les Harder provided to me to show, and it's a satellite image that's been enhanced to show the topographic relief a little more clearly, and you can see that the islands are like bowls that are ringed with levees, protecting the interior of the island from the water and its channels on the outside. Okay, I'll now move on to talking about the effect of earthquakes on levees. One of the big hazards for levees is liquefaction. Liquefaction is not something that our field tests directly address, but I want to present it because we realize that it is a significant hazard. And this is a levee that was damaged in the 1995 Kobe earthquake because of liquefaction of the foundation soils beneath the levee itself. This was a levee along the Koto River. It doesn't look like a levee that you would see in the delta because it has concrete erosion protection on the outside, but inside that concrete is just soil, just like a normal levee. All right, and so what they're walking on there is roughly the crest of what used to be the levee. It has, settled quite a bit as a result of liquefaction. You can see the water is back here in the back part of the picture. This is a flood control levee, and the joint probability of a flood in an earthquake is not very high. So the water level was not at flood level during the earthquake. They could repair this levee to its, pre-earthquake configuration before the flood came along. This is a slide that shows a cross-section of what happened to this levee. The soil beneath it liquefied, and the levee broke into blocks, and part of it sunk into the sand, resulting in that settlement. Now, the effects of liquefaction are not always this dramatic. Sometimes you'll see a few cracks and sand flowing up through them. This is just kind of an example of what can happen because of liquefaction. All right, now I mentioned we're not studying liquefaction. The reason is that from a scientific perspective, we already can predict when liquefaction will happen, and to a reasonable extent, we can predict the effect of liquefaction, settlement, ground deformation. We know much less about the engineering behavior of the peat soil that underlies many of the delta levees. So we focused our attention on the peat, and we deliberately excluded liquefaction. So let's talk a bit about peat. Peat is actually a fairly prevalent soil type. It covers about 2% of the Earth's surface, and it lies beneath many delta levees. We know it's extremely compressible, very soft, and it can be pretty weak too, especially if it's not consolidated to a high pressure, say, beneath the crest of a levee. or something like that. We don't know a whole lot about its earthquake response. We know it's not liquefiable. It won't lose significant strength like the sand will. It already starts out pretty weak typically. But other than that, we don't know a whole lot about it. We do kind of understand the way that the peak might affect seismic waves. So if you have a certain amount of shaking at the bottom, you can predict the shaking at the top. But engineers don't have a handle yet on how that peak might contribute to failures or settlement for the levee. So the National Science Foundation funded our project to do a field test of a levee on peat soil. And before I go on to the field testing, I'll just answer a few questions that often come up related to peat. First, can peat transmit seismic energy? Sometimes you'll hear that the peat has really high damping, and the seismic waves that shake the bottom of the peat will be attenuated, and the top of the peat won't shake very hard. Therefore, the peat will absorb energy and protect the levee from the earthquake. The evidence does not support that hypothesis. This is just one example of the evidence. This is a set of 3 sites that were pretty close together during the 2004 Nagata Chuetsu earthquake. And the 3 stations had different site conditions. One was founded on gravel. One was on gravel with a couple of meters of silt on the top. And then one was on a site that had gravel and silt and then a layer of peat on the top. And these are acceleration records that I'm showing here. The one that was on the gravel had the lowest peak horizontal acceleration, 8 meters per second squared. That's a pretty strong ground motion. It's on the order of about 0.8 G. The recording station on silt was a little bit bigger, about 9 meters per second squared. The one on peat was 13 meters per second squared, so about 1.3 G. That's a pretty big ground motion. Obviously, peat can transmit big ground motions. It has done so in the past. Now, the delta has never been shaken by strong ground motion, so we're forced to look at other areas with peat that have been shaken strongly to learn these lessons. The lessons are teaching us that strong ground motion can indeed be transmitted through the peat.
Are there any accounts from 1906?
We don't have strong motion records from that. So
eyewitness accounts?
There probably are in the Lawson Reconnaissance report, but I'm not aware of those, and I don't know how reliable they would be. You would need a person standing on peat and a person standing close by on stiff soil or something like that to be able to draw conclusions, and it would be, subjective as well. Okay, another question is, have levee failures ever occurred on soils founded on, or levees founded on peat? And the answer is yes. There aren't a lot of these cases that have been shaken strongly by earthquakes, but this is an example published by Sasaki in 2009. And the peat may have contributed in 2 different ways. The author concluded that the main contribution of the peat is that it settled a lot. It's really compressible, so the fill was placed, and it formed this bowl on the bottom. Well, that bowl filled up with water and saturated the sand that would have otherwise been dry had it been in a straight line. And so when the earthquake shook this site, that sand that was saturated liquefied and caused this large deformation of the levee. But if you look at this center block right here that moved down significantly, it's likely that this block may have pushed into the peat or that the peat may have contributed in some way to that deformation mechanism. It's often difficult to know, based on these kind of field cases, what the contribution of the peat is compared with the contribution of the liquefiable sand. So failures have occurred for levees on peat in past earthquakes as well. All right, so now we'll get into the content of our field test. So our motivation was really to isolate the behavior of the peat. We didn't want to have some mix of liquefaction and peat behavior and try and separate those independent contributions. So the first step that we did was to go out with a hand auger and drill into the ground and retrieve samples for laboratory testing. And probably the best way for me to give you a sense for how soft the peat is to just show you a movie that we collected during that site investigation. Okay, so that's me operating the hand auger. The students did most of the hard work. I just got in front of the camera sometimes to make the video. But we reached a point where the hole wouldn't stay open anymore. It was squeezed shut and we couldn't gather samples. So what I'm going to try and do here is just push the auger down without turning it. And so that's going through from about 8 feet to about 11 feet through the peak. And I'm not a very big person, so I didn't take a lot of force to push that down. Now this is in the free field. This is not consolidated beneath the levee. If you put a lot of pressure on the peak, you squeeze out a lot of the water and it does get stronger. So this is about as weak as you'll get for the peak. Okay, and we started doing laboratory tests on these soils, and we've done two different types of tests. One is a triaxial compression test. That's where we take a cylinder of the peak, about that big in diameter, maybe that tall, and we load it up and down this way. And so these are the results from that kind of a test. We've also done tests on cylindrical soil where we shear it back and forth this way instead, and it's important to understand both stress paths because both may exist beneath real levees. Now, we're not the first to have done this type of testing before. Ross Boulanger at UC Davis has done an extensive study of the dynamic properties of the peak, looking at this kind of stress-strain curve to look at the slope of this curve as a function of the amount of strain that's imposed on the soil. What we're doing that's different is that after we do the cyclic loading, the cyclic loading is done with the drain path closed, so all the water that's inside the peak is trapped inside and stays in there. There's no permanent volume change. Then we open the drain path after the cyclic loading and allow water to come out of the peak and reach equilibrium with the imposed pressures. And so after the test, we do a consolidation test. We call it post-cyclic consolidation. And in this case, there was about 2.5% volumetric strain after we opened those drain valves before our data acquisition system crashed and it stopped recording data. We don't know what it would have eventually gone to. It's showing signs of starting to level off. So 2% volumetric strain is a pretty big number. This is consistent with what we would expect from a loose saturated sand after liquefaction. So it's a fairly significant amount of volume change. And the indication is that we should be looking into this at least as a potential deformation mechanism for levees. The amount of volumetric strain that we're measuring is a function of how much shear strain we put into the soil, which is also what happens with liquefaction of sands and with unsaturated compacted fills and other material. We have to go to bigger shear strain amplitudes to start getting volume change with peat, though. In this case, we don't see much volume change until we get out to about 0.2% shear strain. And after we get to that threshold right around here, maybe 0.2 or 0.3, that's when you start getting this increase in volumetric strain. And this volumetric strain would cause levees to settle slowly. It wouldn't be immediate. It would be slowly settling following an earthquake if the shear strain gets bigger than these threshold numbers. All right, so based on that mechanism, we wanted to build a test to look into this hypothesis that cyclically straining the peak may cause settlement. So we constructed a model levee on the interior of Sherman Island. Our original intent was to shake an existing levee that has been there for a long time, undergone all of the consolidation already, but we couldn't find a suitable site where we would potentially damage the levee and the owner would be okay with that. So we deliberately placed our model levee far away from the existing levees because we were also worried that when we're shaking, waves may propagate and shake these levees. I wasn't all that worried about that, but we had to show that our test would not influence the levees, and the best way to minimize influence is to put it far away. So this is a movie that shows how we built our embankment. We constructed our embankment out of geosynthetics and compacted clay, so that black plastic sheeting that you're seeing there is tensile reinforcement. That way we're able to make the levee really strong. And that timber frame is what we mounted our shaker to. So we deliberately constructed this thing to be strong enough to take the force from our shaker and push it down into the peat underneath. We weren't interested in studying the response of this levee because it doesn't look like the levees that are in the delta. It's completely different. Compacted clay, geosynthetic reinforced. It was kind of indestructible. here's what it looked like with the shaker mounted on top. So that this blue metal device is the eccentric mass shaker. The crest height was initially 6 feet tall, and this person here is about 6 feet tall. And so during the 2 months between the time we constructed the levee and the time we tested it, it settled about a foot, which is pretty consistent. That's about what we would predict based on our consolidation tests. So it's pretty amazing. I mean, you can almost see it settling. It's moving so fast. We were able to record the settlement pretty clearly with our data. So I'll show the movie of, this is the biggest shake that we imposed on the levee. You'll see those baskets start to turn. So the concept of the shaker is that these two baskets turn in opposite directions, and they have the same mass, and that mass is at some distance from the center spindle, and that generates an inertia force that will shake it in this direction here. And so it takes a while for it to wind up. As you see it starting to go, you'll notice that the ground surface will start moving up and down, especially at the toe of the model embankment right here and over there. And it looks almost like the model levee is built on a waterbed. So you can start to see a little movement now. And then the frame started rocking back and forth. We were basically maxing out the capacity of our shaker at this point, imposing more force than we had designed the frame for. And so the engineer here turned it off right when it got to the peak level. But you could clearly see dramatic, waves propagating through the ground. So from a geophysical perspective, it was really interesting because you usually don't get to see these things. You look at data, but you could actually physically see the waves. Now, after we did the test, there was no measurable settlement, or no change in the rate of settlement. Okay, the levees are always settling, and the rate slows down over time. We had thought perhaps that our test would cause a change in that rate and cause it to settle more quickly, and that didn't happen. It kept settling basically at the same rate. And there are a couple of reasons for that. First of all, we use our sensors that were beneath the levee to calculate the amount of strain that we actually mobilize in the soft saturated peat. And this is 3 different motions, a small motion, medium, and large motion. The top row shows the entire time series. Most of the motions lasted about 200 seconds, like the one that I just showed the video of. And the bottom is a snapshot of just a little piece of data in the middle, so you can see what the data actually looks like. So for the small motions, we were mobilizing shear strains of about 0.01 to 0.02%. That's clearly too small for us to see any permanent volume change. For the medium motion, we got up to about maybe 0.06. And then for the biggest motion, the one that I just showed the video of, we got to 0.15 or so percent. And I mentioned that we had to get up to about 0.2 or 0.3%. So we were right at the limit of where we anticipate we would start to see some volume change, but we couldn't quite get there. It's too bad we didn't have a bigger shaker. We could have gotten there that way by shaking it harder. So basically what we're showing is that our test was consistent with the laboratory data. Right? We didn't mobilize large enough shear strains to start seeing the permanent settlement. Here's the range of strains that we mobilized in the field test compared to that plot that shows when we start seeing the volumetric strain take off. There are a couple of reasons, though, why we can't conclude that this won't happen for real levees. First of all, there was a boundary condition for our test that's not realistic compared to real levees. The water table is kept at a depth of about 6 feet on Sherman Island just for land use purposes, for farming. Whereas real levees that were dredged directly on top of peat would have been dredged pretty much when it's saturated, then would have pushed the peat down and kept it saturated the whole time. So having this unsaturated, stiff, desiccated peat was an undesired boundary condition. And we think that what happened was that we were shaking the levee and we just couldn't get enough energy down here. This is the material we wanted to study. We couldn't get it down deep enough. We didn't know that that was going to be the site condition. So we did what we could with the site that we had available. The other reason is that for a real earthquake, there would be a combination of strain. Some strain would be from the levee interacting with the peak, but there's also extra strain that's from the waves propagating through the peak. And the combination of those types of strains may be big enough to start causing this mechanism to happen where we start to see the volume change. And to study that, we'll calibrate numerical models to our field test and then extend them forward to real earthquake conditions. And we're also planning a future centrifuge study at UC Davis where we can more carefully control the conditions that we're testing. This is a picture of the centrifuge. And so our model will consist of levee fill resting on top of saturated peak, and we'll shake the base of this thing so that we get the seismic waves and the interaction between the levee and the peak. We can also put water on one side. We can build a flue in the centrifuge and test the liquefaction behavior of the levee fill. Okay, so with that, I think I'll turn it over to Professor Stewart to discuss the Japanese case history. Questions? Are we doing enough time? I guess there's time if anyone has a question or two about the field test. Yes, Bob.
How long was the shaking?
We performed two tests. The first test was in the summer of 2011. We were there for 3 days total shaking. We started with very small level shakes that were intended to just measure elastic properties and make sure our sensors were working, and ended with the biggest ones that we could do. Each shake lasted about 3 minutes or so, and we did a total of maybe 15 in 2011 and 15 more in 2012. The difference between the two tests, by the way, is that in 2012, we built a berm and pumped water into that berm to saturate the peak right beneath the embankment. It looks like it did make a little bit of difference, but not enough so that we got volume change. The peat is not only unsaturated, it's also desiccated and pretty dense. That's why we can walk out there and drive equipment. Otherwise, I think we would sink to our knees. But did that answer your question? All right. Sure.
How comparable were the consolidations in the lab to what you had done in the field under the artificial?
We're doing so the question is how much we consolidated the specimens in the lab compared to what we have in the field. We've consolidated pretty low pressures in the lab because of the field consolidation stresses were small, just to compare with that test. But we've also consolidated to higher pressures than you would expect to meet the real levees too. So we want to cover the full range. It's on the order of maybe 10 kPa up to 100 kPa, something like that.
What kind of volumetric strengths?
Well, the figure that I showed was consolidated at 3 different pressures, and the curves were almost on top of each other. So that it doesn't look like the consolidation pressure. We're still studying this, but that's obviously something we'll look at. But we're seeing similar strengths for the tests we've done at, say, 15 kPa than we are at 40. And they're getting up to 3%. And we're also finding that the cyclic loading is changing the secondary compression behavior as well, starting to reset the clock on secondary compression. So if the levee was built, say, 150 years ago, the settlement rate is now pretty slow from secondary compression, but we're finding that cyclic straining may actually partially reset that clock and speed up the settlement rate again.
Yes, Scott. One comment, the other question. The comment is that in past fragility studies of the delta and the levees, the focus has been on the liquefaction potential of the mineral soil composed part of the dredge, part of the levee embankment itself, or the liquefaction potential of the mineral component of the fluvial portion of the foundation. And for the most part, people have looked at the possibility that the itself would be a problem. Ignore that and consider that to be small risk compared to the other liquefaction. So the folks at your research clarification is really to check that assumption that really the peak itself is minor or possibly not big. Is that a fair statement?
I think that's a fair way to state it. I think in dreams, like 90% of the predicted levee failures were associated with liquefaction and only 10% with failure of organic soils. And those were pretty marginally stable conditions to start with, yeah. Sure.
That's a great lead up to my question, which is, first I must compliment you on telling a great story. But you left out, I think, the most interesting part of the story, which is that having been out there twice, the 2 times you've been to the field, you were actually expecting possible failure of the foundation. You haven't mentioned that here, but it didn't fail. As might have been anticipated from Leslie's remarks and from the testing that Ross Gilmore and others, including Leslie, done, that showed that peats don't develop very much excess pore pressure on the cyclic fluid, although we know they're very compressible and static. So that's the preamble to the question, which is, why didn't you get any observable failure or movement in the foundation other than transient movements, which we all agree were significant, striking?
Yeah, everyone was seasick.
In spite of so much transient movement coming out to the circle of people that were standing around the levees, why was your original substitution that you might get failure of the foundation correct?
Well, we didn't necessarily think that the foundation would fail. We didn't know. We thought it might be a possibility, which is why we tied a chain to our shaker so that we could maybe retrieve it if it did happen to sink in. I was glad it didn't. But that's not really what we were solely focused on. Our main objective was to look at this post-cyclic volume change potential. And the reason we didn't see that is pretty consistent with our lab test data. We just didn't get the strain levels that we needed in the soft saturated peat. I think if we had had soft saturated peat right to the surface or closer to the surface, we could have gotten some of this mechanism happening, because the movements were substantial. There probably were bigger strains right beneath the corner of the levee, for example. It's just that the strains deeper in the profile where the soft material was were not big enough for us to get it because of that 6 feet or so of stiff, desiccated peat. And let's see, you had another question as well in your preamble. I forget what the other part of it was.
That was just one question.
Okay. And did I answer it?
You gave a very smooth answer to it. I think you're rationalizing after the fact.
Well, one thing that did happen after our test was that people were there to witness it, and they said, hey, these guys from UCLA can't even fail this levee. That's good news. The delta levees are all fine. And that was a result of my naivety in dealing with the media, I think, that message got out. That was certainly never the message that we intended. We deliberately did not include liquefaction, which is the biggest driver of potential failures for delta levees, just so that we could study this other really interesting but unknown scientific issue. And the nuance of the science is difficult to convey through the media. So the outcome in the press was unfortunate, and this was never designed as a moratorium on delta levee stability during earthquakes. I think that there is potential for the mechanism we're studying to cause settlement issues. We should be at least aware of the potential for this mechanism to happen.
Certainly, but I would submit that engineers who work in the Delta, while they're not aware of all of the cyclic loading mechanisms, are aware of secondary compression, the fact that heat is very compressible under static loads, and the construction of levees is not a one-shot thing, but a perpetual challenge in maintenance and improvement. levees, I think, are a classic example of rough effects observational method. And that's somewhat opposed to your commendable efforts to do a proper scientific study of these issues. But the issues like secondary compression being awakened after an earthquake, I think was bit on something that was real. But as Les was saying, in the overall context of the Delta, it's relatively small potatoes.
Yeah.
That's a Delta-specific analogy.
we
next to this is up to expand it to show potatoes.
We should move on. I'll just answer quickly and hand it over to John. We never intended for our test to solve the problems in the Delta either. We're testing one site, but it's the first of its kind test. And I would argue that the observational method works if you have observations. And so obviously for static loading conditions, it's great. The Delta levees have not been shaken by design level ground motion. So we can't use the observational method for the earthquake problem. So for the sake of time, I'll hand it over to John. I'm happy to answer questions, after the presentation as well.
Okay, thank you, Scott. So the observational method is a great segue into my part of the seminar today, because I'm going to be talking about observations of damage to levees in Japan. As part of this project, which involves the people on the screen here, we actually looked all over the world, New Zealand, Chile, China, several other places, for evidence of levee damage and earthquakes. And there's been plenty of cases where it's happened, but there's actually very few cases where it's well documented. And when you consider where can you go and get reliable information on the damage and the geotechnical conditions and ground motions, you pretty much narrow down to Japan. And so that's why we're going to be focusing on that. So we're sponsored by Department of Water Resources. Aria, I think, is here. Yeah, there he is. So he's been instrumental in getting this project going. And you see there are collaborators from Berkeley. Les Harder's been involved. And Tsushima Kami is probably one of the most critical people, because without him we wouldn't have had the data that I'll be showing. And finally, Dongyi Kwok is the student who has done the work. So our objectives with this project were to identify the conditions that correlate to damage in levees. So when do we start to see damage and when do we not? And what are the levels of damage that we're seeing? These are principally flood control levees. And what kind of probabilities are we talking about? Are 1% of the levees failing, 50%, 75%? Obviously, those numbers make a big difference. So we wanted to put some numbers to this. So our scope, as I mentioned, was to compile case histories from Japan. And I've mentioned why Japan. Okay? It's because that's where the high-quality data is. Now, Japan has had a lot of earthquakes, of course, and we're going to be focusing on a particular region of Japan that is having earthquakes that are crustal in nature, not subduction zone earthquakes, so crustal earthquakes, and our events are going to be magnitude 6.6, so comparable to the risk here. We're going to look at the post-earthquake field investigations that the Japanese did, the geology. Groundwater turns out to be a big issue. It's not so easy to find the groundwater conditions that you could expect at the time that the earthquake happened. I'll talk a little bit about how we teased that out of the data we had. Ground motions, we're in very good shape in that department. The Japanese have a very dense ground motion network, so we know how hard the ground was shaking. And then all that information gets synthesized together to develop something called fragility functions. Now, I know for most engineers, and maybe virtually all geologists, eyes glaze over when you see words like fragility functions. Let me just say that all that is going to be expressing is the probability of something bad happening as a function of the level of shaking, basically, in this case, PGA. So don't be intimidated by something that seems unfamiliar. This is our study region. As I mentioned, it's on the west side of Japan. This is the east side. Tohoku earthquake in 2011 was over here. That produced a wealth of data of the type that I'll be talking about, but that's not been what we focused on. Those are obviously very long duration motions, 2-3 minutes. We're instead working in this region, which has the crustal earthquakes. And the two earthquakes in particular are this one. This is a projection of the fault to the ground surface from 2004. It's a reverse slip earthquake. And another one here in 2007. They're both in the same region and shook the same system of levees. The levee system is on the Shinano River. Shinano River is the longest river in Japan and has an extensive federally managed system of levees that are there for flood control purposes. There's actually a lot of information on this map. The little circles here are ground motion stations. The red symbols, well, the blue, I should say, are the levees themselves. And then the red symbols are locations where there was damage. The beach balls just indicate the reverse mechanism. These are both 6.6 earthquakes. Also, the Japanese noted cases where liquefaction had occurred. So you'll see plenty of cases where there's damage but no liquefaction, other cases where there's damage and liquefaction. Different damage distributions for 2004, which was on land and occurred directly beneath the levee system, versus 2007, which was off the coast for the most part, and the levels of shaking were lower.
How far was the epicenter from the levee?
Well, the epicenter is actually where the beach ball is. Okay, so this is indicating the focal mechanism, but it's plotted at the location where the slip originated, which is the epicenter. So this was directly beneath the levee system, and this one is a little ways away. Maybe 20 kilometers or 10, 15 kilometers, something like that. This is just to give you a visual of the Shinano River. Under non-flood conditions, this is the river. The levees themselves are here and here. So these are flood control levees. There is usually not water up against the levees. Okay, it happens from time to time, a few times, maybe 2 or 3 times in 5 years or so. But under normal conditions, it's further down. Some areas along the river are agricultural. Some areas are completely unused, and there are some areas that are urban. Okay, so what I'll start doing is going through the different sources of data that we used in our study. This was all collected by the Japanese. In some cases, there had been gear teams that had also been out and looked, and we were comparing their information with the Japanese. But the Japanese was much more systematic. They have engineers who are responsible for certain stretches of the levee, and they know it backwards and forwards. And they literally walk the full length of the levee after a major earthquake. The full length of the river, I should say. This work was done by Shinano Work Office. They walked the full length of the levees. On that map I showed earlier, there were locations marked where there's damage. Where you see no mark, it doesn't mean they didn't look. It just means that there was no visibly observable damage. It fell below a visible threshold. They're recording quantitatively crack depths, at least as far as they can measure, crack widths, offsets across cracks, and subsidence of the levee. I mentioned this already. If nothing is shown, it doesn't mean they didn't look. We really were very careful to make sure about that because it's essential for the analysis we're doing. And they also mapped where liquefaction was manifest. So that would typically be sand boils. There were places where there was liquefaction in the free field away from the levee, and the levee was fine. And there were also plenty of places where there was liquefaction and the levee was damaged. So these are cataloged independently. Now, what we did was we sorted through all this data, and we wanted to group the data into categories. So we have damage levels of 0 to 4, 0 being no damage, 4 being the worst that we see. And you can see the associated crack depths, crack widths, and subsidence levels that go with that. Okay, so this should be 0 to 4 is assigned to each 50-meter segment. The 50-meter segment is important, so we do come up with a discrete number of segments, 50 meters in length, in order to assign a damage level. The levees range, they're about 5 meters tall, 4.5 to 5.7 meters in height. So when we're seeing a meter of settlements, we're talking about 20% loss of height in the levees. That's about the most severe that we would see on any sort of a regular scale. There were some cases worse, but that's about the 90th percentile damage or so that we would see. So it's a very rich data set. There's over 3,000 observations for the levee system in each earthquake. You combine the two earthquakes together, and there's 6,600 observations of damage or no damage, and of course the severity of damage. One of the things we did early, since we have observations of surface manifestation of liquefaction along with the damage, is we just wanted to see for the different damage levels how often there was liquefaction that was evident in that same 50-meter segment. So, as you would expect, if there's no damage, you have a fairly low probability of liquefaction, but it's not zero. It shows that there is cases that things liquefy and there's no damage to the levee. The highest damage, stage 4, we're seeing about 80%. The probability of having liquefaction on the segment that has damage level 4 is about 80%. So most of those really severe damage cases are having liquefaction associated with them. A little bit on geology. We looked at a bunch of different sources. What we finally ended up with was 1 to 25,000 scale maps that were actually prepared for the purpose of managing the levee system by the Geospatial Information Authority of Japan. We needed to come up with some groupings for the analysis that we did, and we ended up with these 3 categories. This would be the most stable: mountain regions, gravelly terrace deposits, essentially alluvial deposits, in number 2 of various sorts, and older river channels and back marsh. And these were actually categories that the Japanese themselves were using, sort of groupings of finer categories, which we adopted. An important point to be made here is that this region along the Shinano River really doesn't have peaks. I think 0.3% of the length of levees had peaks here, so that is not the issue in this study. So this work is not really relevant for the areas of the delta underlain by peaks here. It's more applicable to the flood control levees further east, protecting Sacramento, Stockton, and so on. So this just shows the distribution of the surface geology. This would be what's underneath the levee along the length of the river. We have the Shinano River, and one of the tributary rivers is the Uno River, and the dominant geological condition is the alluvial one, as you would expect. But there's some variations along the length. Okay, so groundwater. This actually was probably what took more time for us to sort out than anything else. So what our objective is with the groundwater is to find the depth of the groundwater on the dates that these 2 earthquakes happened in 2004 and 2007. And so let me go through some of the data resources that we had available to us. The geotechnical investigations that were done after the 2004 earthquake, and the dots here, not these symbols, but the dots here, are the locations of borings that the Japanese did. There's a lot. The blue symbols, by the way, are stream gauges. We'll come back to that. So they did 410 borings. They typically did 3 borings at each station along the levee system. So in other words, you would have 3 borings from which you could construct a cross-section. This is the typical cross-section where the levee is here, and there's different natural formations underneath. They would most often use auger techniques until they got below the water table, then when things started collapsing, they would go to rotary wash. Because of this, we know when water started seeping into the hole, and we have a pretty good feel of water table. They also did a lot of tests where, especially on the sides, not necessarily through the crest, where they would do permeability tests. So they would add water and let the water go down, or they would actually pump water out and let it recover to get permeability. And so through the combination of these two types of observations, we have a pretty good idea of where the groundwater was at the time of drilling. Now, the challenge, of course, is that the water table at the time of drilling is not the same as the water table at the time of the earthquake. One of these earthquakes that happened not very long after a storm sequence. The other one was during more of a dry period. And so we had to figure out a way to take our observations of water level at the time of the drilling and adjust it as needed to the water table that we thought would be there at the time of the earthquake. In order to do that, we took advantage of the fact that we had stream gauges, which I pointed out earlier. There aren't very many of them, but we do have stream gauges, and stream gauge data is available every day. They report it every day, and we were able to get access to it. The problem with the stream gauges is that there aren't very many of them, okay? And we have a lot more levee sections than we have stream gauges, so we need to be able to interpolate. In order to be able to interpolate, we used a few very densely recorded surveys of where the water table was at particular dates in order to build interpolation functions. But we're not just doing straight line interpolation, we build interpolation functions based on detailed measurements. Using those interpolation functions along with the stream gauge data on the date of the boring, we're able to get the groundwater level on the date that the drilling was done. I'm sorry, not the groundwater level, the river water level on the date that the drilling was done. And what we're going to be doing, what we did was we related the water level in the river to the groundwater level. There's a differential there. And we're now taking that differential and applying it to the river water level that we know on the date of the earthquake in order to estimate the water level on the earthquake date of the below the levee. There were a few cases where that didn't work. That's where there's local irrigation practices. So where there's a lot of water coming into the system through irrigation from farming, we weren't using that procedure. It's more detailed than I want to get into, but we did make adjustments for when that was the case. The end result of all that work is we have the location of the water table and the location of the base of the levee. These are elevations. And we take the difference. So this is the levee groundwater elevation minus the levee base elevation. This number is positive. It means the water table is above the base of the levee. If it's negative, it means it's below. And these are our estimates for the right side levee system and the left side levee system for the two earthquake dates, 2004 and 2007. And what you basically see is that for this region down here and a few places in between, we're seeing water above the base of the levee. If we go out here, for example, it's below the base of the levee. So both conditions are represented. Okay, so now we can move on to the ground motions. Densely recorded, the most obvious thing to do with the ground motions is just create a surface called Krigging to interpolate the ground motions where you don't have measurements. The problem with that is that, suppose, for example, I have a recording on rock or something firm, and very nearby is the site I'm interested in, which might be in a soft alluvial soil along a levee. Your estimate of the motion would be strongly influenced by that rock recording, and we know that that's not realistic. So we had to come up with a way of correcting for that. So what we did was we mapped the site conditions along the levee using all that borehole data, and we developed region-specific correlations between the flow count and the shear wave velocity. Those shear wave velocities were then used to calculate a 30-meter shear wave velocity, which is the site term in ground motion prediction equations. We then calculated the difference between the ground motion prediction equation in the data. Those are called residuals. We krigged the residuals. Then we took the krigged residuals, added the GMP back in along the levee, including the site term, which has the proper nonlinearity and so on built into it, and that was how we got our ground motions. And so these are the krigged residuals. It basically lights up with hotter colors when the ground motions are stronger than you would have expected from the GMPE, and it cools down with cooler colors when the ground motions are lower than you would expect from the GMPE. And all these things are very normal. I mean, if you study ground motions, it's very normal to have this sort of variation. And all we're trying to do is quantify it for this particular earthquake. It has to do with deeper site effects and split patterns on the fault that are not captured in the GMP. So as I mentioned, we add the krigged residuals with the GMPE, including its site term, and this is basically showing the PGA along the length of these river systems in the two earthquakes. You can see the 2004 earthquake has stronger shaking levels than 2007 on average. If we had just done direct krigging, that's the black dots. Our methodology, which includes the nonlinearity in the soil, is the red symbols. And I guess the main point to be made here is we have shaking levels that go from about 15% G up to over a G in the 2004, and maybe 15% G to about 0.3 in 2007. Now, on the fragility, as I mentioned earlier, these express probabilities of something bad happening, which is more formally a damage state. So we have probabilities of a damage state, which we're going to plot versus the amplitude of the shaking, which we take as PGA. The most basic way of looking at this, the simplest to understand, is just take any level of damage. If it's moving enough to have observable damage, damage level 1 or more, and just mapping that against PGA. So we'll start with that just to illustrate the process. So what we basically do is we look along the levees and we take bins. This would be for, I think this is actually both earthquakes combined, the data combined together. We bin up the data. Where you see that these bins are very narrow, it means there's a lot of information, there's a lot of sites with ground motions in this region. In order to have all the bins be equal in the number of data points, we have to make the bins narrow. And that was our goal. We wanted all the bins to equal the number of data points. There's a lot of data in here, so the bins end up being very narrow. Data sparser here, so the bins get wider. So all these bins have the same number of data points, and it's showing the number of damaged segments. Or if you take that and divide it by the number of data points per bin, you get a probability, and it's showing the variation of essentially probability of damage versus PGA. The two plots are actually showing the same thing. This is just a linear scale for PGA, and that one's a log scale. This is taking the same thing and now just plotting symbols, and we fit a function to it. We use various functional forms. We end up using the log normal CDF, which is a cumulative distribution function. Just as a way of fitting it, that function has some physically meaningful parameters, which is why we picked it. Okay, so that tells us the basic fragility, and actually before I leave that, I should just point out what we're looking at here. So, you take this region in Sacramento, maybe we have 0.1 to 0.2 G ground motions. These, we're looking at numbers less than 5%. That means less than 5% of the levees, 50-meter segments of levees, would have a damage level that would, get to 1 or more. Obviously, Japan goes a lot higher, but these are the ground motion levels we're looking at. So it's not zero, but it is fairly small. But keep in mind, this is only for 50 meters. So we're looking, obviously, in a river system as a whole with many subsegments. We did look at many other factors to see how they affect the position of that fragility curve. We looked at geology, it ended up not making a very big difference. We looked at water, and also some other issues related to the shape of the levee, which I won't go into. I'm just going to show the one that really did matter, which is the depth of the water table. So if we group the data into basically shallow depths and deeper depths, and there are various thresholds for how you can define that, what you basically see is if the water table is, let's say, above the base of the level, base of the levee, this would be dW greater than 0, those are the red symbols, and we see the fragility is coming in higher. Whereas if the water table is deeper, we only look at that data, then the fragility comes in lower. And you can use different thresholds, you see the same trend consistently. The other parameters we looked at didn't show these sorts of consistent, robust trends. The water table seems to be the most important parameter affecting the fragility. Shallow groundwater leads to higher fragility, meaning higher rates of damage. Deeper leads to less damage, which is what we expect, of course, from a liquefaction point of view. So then, this is the last set of fragility plots I'll show. Then we looked at, well, those are just the occurrence of damage at really any level. Now if we look at the occurrence of damage that have become more severe. So this is more than 1, so 2, 3, 4, more than 2, so 3, 4, and more than 3, which would be just damage level 4, the most severe. So the same format, probability versus PGA, and these are actually conditional probabilities. So these are only taking the subset of data where there was damage. So we condition on damage having occurred, and then we look at the probability of exceeding these damage states. And the interesting thing that comes out here is when the groundwater is deep, you retain this PGA-dependent fragility, which we think is coming about because a lot of those are related to slope instabilities. And of course, if you shake it more strongly, you're going to have a higher probability of some displacement occurring. When the groundwater is shallow, a lot of this is happening in connection with liquefaction. And there really is no trend, particularly in the data. So once you get strong enough to liquefy, the damage doesn't seem to correlate very much with the level of shaking.
Do you look at anything other than PGA in terms of ground motion parameters?
Yeah, so the question is, did we look at ground motion parameters other than PGA? And no, we have not done that yet. But the thought has crossed our mind. And then the last point that I'll make is with AREA's help, we were able to get data from various regions in California, which are shown here, which we call north, central, south. So these are locations of borings that were done along levees. And the goal of this was just to see, do the geotechnical conditions that we were studying in Japan have a relationship to what's going on here in California, not including the delta. And so this is pie charts of soil type. So basically, these are the different regions in California, north, central, south, and this is the region in Japan. And the main takeaway here is that the regions in California have more fine-grained soils, particularly clays, than the one in Japan. Okay, so Japan has only 10% clays, 24-25% silt, and more gravels and sands. Then, but all these soil types are represented, and there's large volumes of data in each. And so then we look at histograms of the N160 low count within the different soil types, being fully aware, of course, that low count has very little meaning in clay. Since things are often taken out of context, let me be clear on that point. I'm not advocating the use of low count in clay. But just as a relative indicator of stiffness in the different regions, we're showing this. And so these are the foundation soils, and these are the 3 regions in California, these 3 rows. This is in Japan. And the main takeaway here is that if you look at the fine-grained soils, California's are on average stiffer. We see the histograms going out to higher low counts and having larger means than in Japan. Okay? So when you look at the sands and the gravels, which are relatively sparse, particularly in California, the numbers are more comparable. So the next step of our work, aside from the ground motion issue, which is something we may look at, The issue is how much can we do before the student graduates? We run out of funding. We want to do geotechnical analysis of the cross sections in a sufficiently simplified way that we can get through a large number of them. And the idea here is that instead of looking at PGA, why don't we look at a metric of damage that we as geotechnical engineers would use? So it could be something like the probability of liquefaction, or in cases where we don't have liquefaction, because there's a lot of stretches of the levee in Japan where that's the case, we might look at a computed Newmark displacement, something like that. So can we come up with a parameter of the demand that is more geotechnically relevant, takes into account the types of things that we do, and then see how that relates to the actual rates of damage? Because we often assume as geotechnical engineers that when we run our analysis and we compute a displacement of, say, 50 centimeters, that that's what's actually going to happen. So what is the relationship between these computed demands and what actually has occurred? That'll be our next step. A lot of those calculations have been done, but we haven't had time to sort through them and make sense of them. So these are the conclusions of the talk as a whole. The first one is related to Professor Brandenberg's portion of the presentation of post-cyclic volumetric strain. So you're familiar with that. I think the main bullet points for mine would be that we're seeing clearly in the data that there is an increase in fragility with amplitude shaking and with shallower groundwater. And the numbers themselves are interesting. So when we have about 15% G, we're looking at about a 3% fragility when the groundwater is shallow, and about a 1% fragility when the groundwater is deep. Those are small numbers, but again, keep in mind, these are computed on the basis of 50-meter segments. There are many such 50-meter segments protecting any given urban region. And so, as we take that in aggregate, the probabilities, of course, would grow. So, with that, I will stop and take the next round of questions. See if you're friendly. Yes?
In urban areas that are subject to seismic activity, people are required when they get loans backed by the federal government to get earthquake insurance. Is anything that you're seeing here indicate that that should become a requirement in the Delta area or in Sacramento?
I guess the question would be whether the earthquake insurance would cover flooding in the event of a levee failure and subsequent inundation. I doubt it would. I think the standard CEA insurance is for shaking loss, so I'm not sure about that.
But what I'm getting at is what you're talking about the shaking that was not the cause of levee to fail. I would think that same amount of shaking is causing outcomes.
Well, so that's a different question. If we're talking about 15% G shaking, how often are houses damaged by that? Pretty small percentage of the time, in my experience. I wouldn't be too worried about that in the absence of ground failure. If I was living along the river in Sacramento, I would be more worried about the potential for that levee to be unstable anywhere along its length, because if it fails anywhere and the water is up against it, and that is a big if the water up against it, then you could have inundation.
That kind of leads to my next question. The levees in Japan that we're looking at were not levees that were always wet. And I wonder what difference that makes with the water table you're trying to measure.
Yeah. Well, it makes a big difference. So if the water level is up against the levee, as it is in the delta, that is a much worse condition than if the water level is deep below the toe of the levee. So the picture I showed you, the water is fairly far down relative to the base of the levee. Now, the groundwater might be a little bit higher. But the condition we have in the delta is actually much worse than what we studied in Japan from that point of view. Now, if you look along the flood control levees in the urban areas, it is more comparable to what we have in Japan. Most of the flood control levees are not constantly retaining water in the urban areas. So we have to distinguish the delta region from the flood control levees further to the east. Yes?
Ditch
case places in Japan where you have peat in the substrate. Hokkaido has big areas of peat, for example, and has I don't know if they have levees out there, but and then they can do this kind of work. It may be a slightly different kind of earthquake, but still, if you get some experience out there.
Yeah, the question is, do we have cases in other parts of Japan, like Hokkaido, where there were peats underneath the levees? And the answer is yes. As you mentioned, Hokkaido has it. We have not looked at that data yet. The data is a little less robust than the region we studied. The ground motion network is more sparse and so on. But our colleague, Nakami, who I mentioned, is starting to gather this information from the local levee officials up there. So depending on what AREA tells us to do next, that may be a high priority for us. But the data does exist. We haven't looked at it really yet to draw any conclusions.
Yeah. For the earthquakes you studied, they were both reverse, but geographically separated with respect to your river area. Was there any effort made to analyze any directivity in their ground motion release? Or you just take what you recorded and went from there?
There was directivity, most definitely.
I thought I saw some.
So this is the Krigged Residuals. So again, this is basically the difference in log units between the ground motion as reported and the median that you would expect from a GMPE. And this is a GMP that was overall unbiased, so on average it's doing pretty well. And so what we're seeing here, there's evidence of directivity, but it's, I don't know, maybe not directivity in the sense that we would normally use that term. So if you take, for example, this 2007 earthquake, it's rupturing up here, and the areas that are lighting up are over here. This is not where you would expect directivity. Directivity should have been here, right? So there are local regions of amplification relative to the GMP that we can't necessarily understand. Here again, we're off to the side. I'm not sure I would call it directivity, but there's just peculiarities of the source and the path that make it light up, but not the classical directivity of the Somerville-Davidson side. We often don't see a lot of that in reverse earthquakes. You know, it's more pronounced in start and slow.
I think that concludes the questions. If you guys have further questions, like talk to speakers afterwards. Thank you for coming, and that was a really great seminar. So for the rest of the audience, we have upcoming seminars that you guys should attend. On July 17th, we have Roger Faulkner from Cardiff University, who's presenting on the Severn Barrage, which is Europe's largest proposed marine renewable energy project. And then on July 29th, Neil Hughes will be presenting on water property rights and markets in the Australian Marine Darling Basin. So if you want further details, you can go to our website and check out the schedule for those brown bags. And thank you all for coming. Thanks to the speakers again.